Physics is the story of our quest to understand the universe. From the early ideas of ancient philosophers to the groundbreaking theories of modern science, physics has evolved through the centuries, reshaping our understanding of nature and our place in the cosmos. In this video we cover the four eras: the birth of physics, Renaissance physics, classical mechanics, and modern physics. Physics didn't begin in labs or classrooms. It started with people gazing at the stars, asking questions about the world around them. How do things move? Why do they fall? Let's go back in time to explore the origins of this fascinating science. The earliest physicists weren't scientists as we think of them today. They were farmers, architects, and astronomers, observing the natural world. The Babylonians tracked the movements of the stars, creating the first calendars. Egyptians used the stars to align their pyramids. In India, the philosopher Kanada introduced the idea of the Parmanu, indivisible particles that form the building blocks of everything. Around the same time in Greece, Democritus called these particles atomos, planting the seed for atomic theory. The Greeks were among the first to seek natural explanations for natural phenomena. Thales of Miletus, often called the first physicist, believed that everything originated from water. Pythagoras took things further, linking mathematics to the physical world. He believed numbers could explain the universe, an idea that still forms the foundation of physics today. One of Pythagoras' most famous contributions is the Pythagorean theorem, which states that in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. This principle not only shaped geometry but also has countless applications in physics and engineering. Aristotle proposed that the terrestrial sphere was made of four elements: earth, air, fire, and water. Meanwhile, the celestial spheres were made of a fifth element, an unchangeable ether. Objects made of these elements had natural motions. Earth and water tended to fall, while air and fire rise. The speed of these motions depended on their weights and the density of the medium. Aristotle also argued that a vacuum could not exist, as speeds would become infinite. While his geocentric model of the universe was later disproven, his systematic approach to science influenced generations of thinkers. Finally, Archimedes, a genius of mechanics, discovered the principles of buoyancy and leverage. His famous Eureka moment came when he realized how to measure the volume of an irregular object. During the Hellenistic period, Eratosthenes made history by calculating the circumference of Earth with remarkable accuracy, using just sticks and shadows. Later, Ptolemy Almagest became the definitive guide to the geocentric model, shaping astronomy for over 1,000 years, even though it was ultimately incorrect. While Europe entered the so-called Dark Ages, the Islamic world became a hub of scientific innovation. Scholars translated Greek works into Arabic, preserving and expanding upon ancient knowledge. One of the most influential figures was Alhazen, or Ibn al-Haytham, who wrote the Book of Optics. He revolutionized our understanding of light and vision, establishing the foundation of modern optics. Al-Biruni and Al-Kazini explored mechanics, gravity, and even concepts of density and balance. Their contributions would inspire future scientists across the world. Eventually, these works made their way back to Europe, igniting a renaissance of scientific thought and laying the groundwork for the scientific revolution. From the ancient skies to the Islamic Golden Age, these early thinkers shaped our understanding of the universe. Their ideas, even when flawed, inspired generations to seek the truth about our world. The Renaissance was a time of rebirth, not just in art and culture but in science. It marked the beginning of a new way of understanding the natural world, setting the stage for the scientific revolution. The Renaissance era was characterized by a shift in thinking. Nicolaus Copernicus was one of the first to challenge the ancient geocentric model, proposing instead that the Earth and planets orbit the Sun in his revolutionary heliocentric theory. Nicolaus Copernicus proposed that the Sun, not the Earth, is at the center of the solar system. This idea challenged centuries of Ptolemaic tradition and sparked debates that forever changed astronomy and physics. Galileo Galilei furthered this revolution by using the telescope to observe celestial phenomena, such as the moons of Jupiter, which supported the heliocentric model. He also discovered the principles of falling bodies and the motion of pendulums, laying the groundwork for classical mechanics. Galileo's telescope revealed the imperfections of celestial bodies, such as craters on the Moon, and discovered Jupiter's moons, proving not all celestial objects orbit the Earth. Johannes Kepler built upon these ideas with his 3 laws of planetary motion, describing the elliptical orbits of planets, their varying speeds, and the relationship between their orbital periods and distances from the Sun. He emphasized the importance of mathematical precision in physics. First law: planets orbit the Sun in elliptical paths, with the Sun at one focus. Second law: a line joining a planet and the Sun sweeps out equal areas in equal intervals of time, meaning planets move faster when closer to the Sun. Third law: the square of a planet's orbital period is proportional to the cube of its average distance from the Sun. René Descartes introduced a mechanistic view of the universe, seeing it as a machine governed by physical laws that could be understood through mathematics. René Descartes argued for a universe governed by mechanical laws, where phenomena could be explained through cause and effect. The Renaissance wasn't just an era of artistic brilliance, it was the dawn of modern physics. By challenging ancient beliefs and introducing a scientific approach, Renaissance thinkers paved the way for the scientific revolution and classical physics. Which Renaissance breakthrough do you find most fascinating? Welcome to the era of classical physics, a time when the laws of nature were meticulously studied and quantified. From the mysteries of electricity and magnetism to the principles of energy and motion, this period shaped the modern scientific world. Classical physics began with Sir Isaac Newton, who formulated the laws of motion and universal gravitation. His work provided a framework for understanding the motion of objects both on Earth and in space. Isaac Newton's laws of motion explained how objects move and interact under the influence of forces. His law of universal gravitation described how celestial bodies attract each other, revolutionizing astronomy. Benjamin Franklin's experiments with electricity laid the groundwork for a deeper exploration into electromagnetism. Benjamin Franklin's studies on electric charge and Alessandro Volta's invention of the electric battery. Michael Faraday's discovery of electromagnetic induction and James Clerk Maxwell's equations unified electricity, magnetism, and light into a single theory, transforming our understanding of energy. Maxwell's equations, which unified electromagnetic theory. Maxwell's equations are a set of 4 differential equations that describe how electric and magnetic fields interact, and how they are generated by charges and currents. Sadi Carnot's work on heat engines laid the foundation of thermodynamics. A Carnot cycle is defined as an ideal reversible closed thermodynamic cycle. 4 successive operations are involved: isothermal expansion, adiabatic expansion, isothermal compression, and adiabatic compression. During these operations, the expansion and compression of the substance can be done up to the desired point and back to the initial state. James Prescott Joule demonstrated the conservation of energy. Ludwig Boltzmann developed statistical mechanics, explaining entropy and molecular motion. Thomas Young's double-slit experiment proved the wave nature of light. Christian Huygens and Augustin Jean Fresnel advanced the study of optics and wave interference. Classical physics provided the tools to understand the universe in ways never imagined before. Its principles are the backbone of modern technology, from engines to electromagnetism, and laid the groundwork for quantum mechanics and relativity. While classical physics is not the end of the story, it remains an essential chapter in humanity's pursuit of knowledge. Welcome to the fascinating world of modern physics, a period that has redefined our understanding of the universe. From the mysteries of quantum mechanics to the wonders of cosmology, modern physics continues to push the boundaries of human knowledge. In 1905, Albert Einstein introduced the special theory of relativity, revolutionizing our concepts of space and time. A decade later, his general theory of relativity described gravity as the curvature of space-time, leading to predictions of black holes and gravitational waves. Quantum mechanics emerged to explain the behavior of atoms and particles. Pioneers like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed a framework that challenged classical physics, introducing phenomena like wave-particle duality and quantum uncertainty. The discovery of subatomic particles like protons, neutrons, and electrons led to the development of the Standard Model of particle physics. In 2012, The confirmation of the Higgs boson at the Large Hadron Collider marked a monumental achievement. Modern cosmology explores the origins and evolution of the universe. From the Big Bang theory to the study of dark matter and dark energy, astrophysics uncovers the deepest mysteries of the cosmos. Modern physics has transformed society through technological advancements like semiconductors, lasers, and nuclear energy, driving innovation in countless fields. The discoveries of modern physics have shaped not only our understanding of the universe but also the technologies we rely on every day. From quantum computing to space exploration, the future holds limitless possibilities. As we continue to explore the mysteries of nature, modern physics remains a guiding light in our quest for knowledge. The history of physics is a testament to human curiosity and ingenuity. It reminds us of how far we've come and inspires us to continue exploring the mysteries of the universe. Thank you for joining us on this incredible journey through the history of physics. Don't forget to like, share, and subscribe for more explorations of science and discovery. See you in the next video.